Welcome! Today we are going to see how to efficiently manage our RHEL edge devices by using the GitOps methodology and taking advantage of Ansible Automation Platform event-driven automation features. In multiple scenarios, there is a need to deploy applications close to where data is generated, due to factors such as limited connectivity, bandwidth, or latency, and sometimes to avoid the high cost of sending data to the cloud or the data center. In such cases, we encounter unique challenges related to compatibility, security, and specifically the scale of the solution. Edge computing solutions often involve deploying and managing numerous small devices. It can get even more challenging when you think about deploying devices in remote and costly to reach locations like windmills or offshore oil platforms or even satellites in the space. To address these challenges, you will need highly smart automated solutions that will enable you to manage those devices' lifecycle seamlessly, even without direct human intervention, ensuring consistent configuration and behavior across a large scale. Today, we will explore how to achieve this consistency using GitOps approach, and how you can simplify the lifecycle management in edge locations with the help of features available in OSTree image-based RHEL systems. Now, let's review the architecture for this demo. We have 5 key components in our setup. A source code repository, in our case GT, where we store configuration files. Ansible Automation Platform, which automates the entire solution lifecycle. An image builder responsible for creating the RHEL images for deployment at the edge location. Slack, which we will use for notifications, and finally the end device that provides the actual service. In this demo, I run GT Ansible controller and the image builder on the same RHEL VM running on my laptop. Additionally, we will create a new VM to act as the end device at the edge. Now that you are familiar with the architecture, let's dive into the demo. These are the steps that we are going to follow during the demo. We'll start by making a change in Git, which will lead to the creation of a new RHEL image. Next, we'll deploy this new image to the end device. You will see how it registers itself in Ansible Automation Platform and fetches its desired configuration from Git. Later, we'll take a look to the containerized applications running on the edge devices. You will see how we can offer serverless self-healing applications with automated updates using just Podman. Additionally, we'll explore how to deploy new containerized applications in a descriptive way without using Kubernetes. In the next step, we will introduce changes in the configuration by modifying a file in Git. We will demonstrate how these changes are automatically applied to all systems. We will also try to manually override the configuration of the end device, and you will see how Ansible Automation Platform enforces the Git-based configuration, removing any manual alteration. In the final step, we will intentionally make a change in our image definition that disrupts the self-healing mechanism. You will observe how the RHEL system detects this issue and automatically rollbacks to the previous working version while sending a notification to Slack. Are you ready? Let's get started. First, we want to create a new RHEL image, and we have 2 options for doing this. The first is through console.redhat.com, but we'll choose the self-provisioned image builder installed on a RHEL VM. However, we won't interact with the image builder directly. We'll be following the GitOps methodology, which means that we have a source of truth, typically a source code repository like Git, where we host the desired configuration for our environment using descriptive configuration files. Instead of configuring the image builder directly, we created a file that describes our desired image, including user settings and software packages. To ensure that any changes in this source of truth are applied to our environment, we created a webhook in Git. When a change occurs, the Ansible controller automatically enforces a new state by creating a new image using the image builder and publishing it so the end devices can use it. Let's see this in action. We'll start in our source repository Git, where we have 3 different repositories. The one containing the image description is here. In our case, we have 3 files: the image description, the Kickstart file for the first boot automation, and a file to select the image version to be published. Let's review the image description file. Here you can see that we have several packages included in our image and a new user named Ansible, which is on the serverless group. Let's introduce a change in this image definition. For example, let's include here the bind utils package. As soon as I press here commit change to push the new version to Git, a webhook will be launched, which will start a job in Ansible controller. So let's review the active jobs in Ansible controller and press commit changes in our source repository Git. Okay, I already commit the change. So in few seconds, we will see how the webhook start that workflow in our Ansible controller. As you can see, in the meanwhile, we can check the settings to see the webhook. The webhook is pushing to the endpoint of event-driven automation. And there we go. We have here a new workflow and a playbook run. We can see here the workflow. So as you can see, first it will create a new image, a compose image. Then it will for me to approve the publishing of that new image, and finally it will run a new later a new job, Ansible job, which will publish the image. Let's wait for the compose image job to finish. Okay, the compose image job is about to finish. The actual playbook that is behind this job is simple because I'm using the Ansible collection that manages image creation in the image builder. Let's take a look to the image builder. We can use Copic to have this UI and review what's going on in the image builder. As you can see here in the image builder menu, we have this new blueprint. That's the one that we are using to create this new image for the edge. We can also check the packages. We see here bind utils. That's the one that we included in our Git repo. And here we can see the list of images that has been created. It's still building because the job is about to finish, but it's not yet finished. Let's wait some seconds more to have it done. And it's done. The time that it takes to create the image will depend on the resources of the image builder. So now our workflow is waiting us to approve the next step. We can also see that we configure notification into Slack. So everybody in this channel will take a look to the Slack and see that the Ansible Automation Platform is waiting for approval to continue with this workflow. So let's approve this job. As soon as I approve, we can double check that our job will continue publishing the image. Let's wait for this to finish. This will take much more or less time than compose image. And now the publish image job has finished. So we have our new image created and ready to be used. With this, we have completed the creation of a new RHEL image using the GitOps approach. By following this methodology, we get the GitOps benefits such as increased reliability and stability due to the Git's rollback and version tracking capabilities. All of this is possible thanks to the image builder, which allows us to create images in a descriptive way, and Ansible Automation Platform, where we can configure event-driven automations as seen in this workflow, making it possible to adapt the platform state to changes in the environment. Now, let's move on to the next step. In step 1, we created and published the image by putting the OSTree bits into a web server that is installed in the Ansible controller. Now, we are going to deploy that image into the end device. In my case, I'm using a custom ISO that points to the right URL where we publish the OSTree image. However, this process could be even more automated by booting the device directly from network, eliminating the need for creating a USB with the ISO image. Let's do it. First, I will create the ISO. So I will go to here to templates, create ISO kickstart here and launch it. The custom ISO is just the regular RHEL ISO with a custom kernel argument that makes the installer to look for a custom kickstart in the image builder VM. The same kickstart file that we have published. The good thing about this is that I don't need to generate a new ISO if I change the kickstart or if I change the OSTree image, since the only configuration included in this ISO is the web server URL running on the image builder. Let's take a look. This is successful, and here I included a debug message with the actual URL where we can download the ISO. Let's download it. I've already downloaded the custom ISO into my laptop, and I will use it to create a new VM. I'm using libvirt in my laptop. I will create this image using the ISO. Select the ISO that I download. It detects that it's RHEL 9.2. I will add here one dig more and name as n device, and that's it. It will start from the ISO, and then you will see how, without any human interaction, the operating system installation will be launched. And then once the operating system has been installed, the system will reboot and then send an event notification to the Ansible controller. The controller then will start an automated onboarding process, which is a workflow with multiple jobs in the Ansible controller. We will see that jobs in the controller. So let me open here the running jobs in the controller. So you see that the workflow is launched as soon as the system reboots after installing the operating system. Let's wait a little bit. So Anaconda installer is almost complete. Okay, now Anaconda is running the post installation steps. So it reboots. It will start now from the local hard drive instead of the ISO. And then we will see how the Ansible controller starts thanks to event-driven automation, this new workflow that will perform the onboard of this new end device. Let's wait a little bit because it's in the actual kickstart file with several steps, several commands that I included in the kickstart, and I think the webhook is the last one, so maybe it takes a little bit more time. Okay, there we go. Here we have our workflow. We can see here that it creates a new host in the inventory in the Ansible controller, test connectivity, and start the device configuration, which in this case is just changing the host name, but it will also trigger more configurations for the onboard process, as we will see in next steps of the demo. In this step, we have seen a fully automated onboard experience, and now we have a ready-to-use end-device system included in Ansible Automation Platform for lifecycle management. This means that you won't need to send specialized people to various locations, saving time and reducing cost in many cases. Now, with our systems installed, let's start using them. When we consider applications in the edge computing scenarios, we find a wide variety of options. However, for such applications, we need the platform to meet at least 3 key requirements. First, edge devices often have limited hardware resources, so applications on the platform must consume as few resources as possible. Second, applications should be fully automated, including upgrades. And lastly, applications should be resilient, capable of recovering from critical failures. While similar capabilities might exist in public clouds and data centers, the hardware used in edge computing solutions is different. Due to hardware limitations, deploying a full Kubernetes cluster, which is common in data centers when you want to deploy a serverless application, for example, might not be feasible in these scenarios. Here, we must consider trade-offs between capabilities and hardware resources consumed by the platform. One solution is to use just RHEL and Podman to achieve similar capabilities at a fraction of the resource cost. Let's look at it. We have 2 test applications deployed on our end system, both as rootless containers. One of them is a simple HTTP server, and the other one is a web browser game. Let me show you something. If I jump into the end device and take a look to the running containers, I just see one. That's because the other one, the HTTP server, has been deployed as a serverless application, which means that then any container will be running until someone wants to use the service. So let's try to use this service, which is published in port 8080 in this end device. As soon as I try to query the service, we will see a new container image has been launched here. Let's see it. See, as soon as I try to reach out to the service, this new simple HTTP container has been created. And it's quite fast, as you have seen. I get the answer as soon as I try to query the service. This is great because we won't be wasting any resource from our edge device until someone wants to use this service. Remember that in edge computing use cases, most of the time we are really constrained in resources in our end devices. If we wait a little bit more, one more minute, this container will be stopped because nobody is querying the service anymore. So it's not just that the container is not running when we start and then it will be run when the first one that want to reach out to the service tries to get an answer. Is that when nobody is using it, it will stop the container and we will start saving resources. Okay. Besides that, we also mentioned that fully automated lifecycle management is a key aspect. So if you create a new version of the container image and push it into the registry, 2 options exist in order to automate this upgrade. You can configure a webhook in the container image registry to start a workflow in Ansible controller, as we have seen in other steps. Or, as second option, you can use Podman feature called Podman Auto Update to check the registry for updates and apply them automatically. In our case, we will be using the second option. I will update my game app using Podman Auto Update. But first, let's check out the actual application. This is the application running on port 8081. So you probably notice a problem here with an embedded image that is not loading. So I will try to fix it updating the image. The good thing is that right after publishing the new image, Podman Auto Update will deploy it. But what could happen if I, for example, I create that new container image and I introduce an error that prevents the app from starting? Well, that's not an actual problem because Podman Auto Update detects this and automatically rolls back to the previous container version. Okay, let's test it. Let me open my container image registry. For this demo, I'm using Quay.io, a SaaS service running on the cloud, which is a container image with advanced features like on security scans for your container images. This is my container image for the web game, and as you can see, I have 4 labels. I have version 1, 2, and 3, and one special label prod, which is linked to one of the previous ones, and which is pointing to the version that will be deployed on production. At this moment, we are running version 1, the one which has this problem with the image that is not loading. I already created a version 2 where I included a mistake, a problem with the entry point. As you can see, I misspelled Nginx. So this will prevent our container to be running on our system. So if I try to deploy this container image, it won't work. Now I will change production label to point to version 2. So Podman Auto Update detects that there is a new version. This is the same that if I would just push the new version to the container registry, moving this label. So Podman Auto Update will trigger that new update, just pull the new image and put it into production. But we will see what happens when it does not work. In order to track what's going on the end system, let me open the console here and let's use this command to watch what's going on. I will Podman Auto Update dry run, which will show up if Podman is triggering a new update. I will just use echo empty, so it's easier for us to see the difference between both commands. So first I have here the Podman Auto Update command and the containers running on my system. This is the actual container that we will be updating. It has been running for 2 hours now. So let's update the image. As I said, instead of pushing a new image, I just move the production label to version 2. New label. I will put here prod. It detects that already exists, and I will move. Then we will see, there we go. We have updated, pending. Podman Auto Update, as soon as I use a new version for label production, it detects that it needs to pull the new container image, and we will see how it tries to run the container with the new version just in few seconds. But remember that we intentionally introduce a mistake in the image, so that image won't be able to start in our system. And what we will see is that once Podman tries to run it, so now we have the new version running for 5 seconds. Since this version is not running, what it will do is just automatically roll back to the previous one. Oh, there we go. So now it tries to run again the previous one, and it will try again the update until it completes successfully. But the good thing about this is that if I go here and try my actual image, I can use it. So this is let me, to be sure, I will open a new incognito window. So you see that I'm still able to use the service, even though the version 2, which is the one that I publish, has an error that is not able to the container to run. So now I will move to the version 3, which solve this misspell of nginx and solve the issue with the image. So go here again, move prot move tag, then Podman auto update will detect it. We will wait a little bit so the new version is up and running, and hopefully what we will see is that we get the application, the web browser game, not yet there, so it's still pushing probably the image. Let's wait a few seconds more, and we will see how the new updated image with the right embedded image is showing up on my web browser. There we go. So now, as you can see, we are running a container for 3 seconds. So hopefully this is now the new version 3. See, we have now our updated image with the right image showing on my web browser. Both the HTTP server and the web browser game were deployed in all end devices by default as part of the onboarding process. But what happens if I need to deploy a specific app in a specific device? Well, you can configure filters in the event-driven automation that detects that the right device started and then perform the installation. Or you can just perform the app install as a post-deployment step manually. Let me show it to you. I created a job template, a job in our Ansible controller here that uses a file descriptor located in Git to deploy a new app. This is the actual template, and let me show to you the content of that file descriptor, which is right here. As apps, I have here this descriptor that will create a systemd pointing to a Podman which will run this container. But as you can see, it's all in a descriptive mode in this file. I will now run the job. Once I launch it, it asks about the device where I should install the application. And this Ansible playbook will copy this descriptor with the information about the image of the container and publishing port into the right location in my end device, and then just restart the systemd in systemd units. The systemd will start Podman with the right image, which is an actual SCADA open source project called Fuchsia on port 1881. Now the job finished, so let's try to use the new application. The port is 1881. There we go. So this is the actual application where we can deploy our own project. For example, let me open this project, and you have an idea. Here we don't have any integration. We cannot get any information on the end device because this is just a VM running on my laptop, but you get the idea of how to deploy a specific application manually using Ansible Automation Platform in one specific device. You have seen how RHEL and Podman make it possible to include complex deployments like serverless applications with up-to-date and self-healing capabilities on small hardware footprint devices. This means that you don't have to sacrifice useful features and you can make the most out of your hardware. This flexibility is even greater if you think that with RHEL you can not only deploy traditional or containerized workloads with Podman, but also deploy applications on top of low-resource Kubernetes cluster, thanks to the addition in Red Hat Device Edge of the support of Microship, an upstream Kubernetes project that includes some of the OpenShift APIs designed to be executed in small hardware footprint devices. In summary, it's all about deciding where to place your workload and how you want to run it. Now, let's move on into the next step in our demo. Managing device configurations at scale is not easy. There is always a risk of config drifts between systems or config version mismatch. We need to enforce a consistency in our platform. Otherwise, we could head into situations where the behavior of our solution is not the expected. By using GitOps, where we have a single source of truth for all our configurations, we can rest assured that the config drift won't happen in our environment. And with a little bit more configuration, we can even prevent the case that someone manually misconfigured something on the end device. Let's see how it works. We have our configurations in the source code repository. In our case, as an example, we have 3 files. The RPM OSTree.conf that configures how OSTree updates work. The Greenboot file is the system image auto rollback configuration, and the serverless file. Let's say that we want to enforce password authentication for sudo users. At this moment, if we check the current configuration in the device, sudoers, we have that users don't need a password to run a sudo command. Let's check this out. Echo hello. Okay, so I want to change this, which is a good idea, by the way. So instead of configuring system by system, I just will change the file in the source code repository here. That, as you can see here, we also have the same configuration. So I will change this now, and I will put here. Just remove this comment this out, and I put here a comment. Change it. Okay, as soon as I commit the change, remember that we use Ansible event-driven automation. So with a webhook, we will see how a new job is launched here. So let me do it now. Now I changed the file in the Git. Of course, I'm using the web browser for convenience, but you can just use Git push from your local system. So now the webhook reach out to the IDA service, then launch a new workflow, and then here, if we double check again the configuration, we should see that the file has been changed, and now hopefully I need a password for running the command. Okay, we have all our end devices configured in the same way. But what happens if someone like me with privileges go to the device and reconfiguring this setting manually to remove the password authentication again? Well, I configure a simple Python script using inotify that monitors change in /etc. And if it detects that someone creates, change, or delete a file, it notifies that to Ansible controller, who will enforce again the configuration that is in our source code repository. Let's try it out. Okay, so now I will modify the sudoers file. Sudoers file. Okay. Go to the end, and here I will comment this out and comment no password, and I will put here a comment that it's manual. Okay, let me put here the Ansible controller jobs. So once I write the file, my Python script will send this notification to Ansible controller, which will start again enforcing the configuration again on this system. So now let me double check again. Sudo ers file, and see, we don't have my change here. You have seen how powerful is the usage of event-driven automation, since we have made a solution that adapts to events such as someone trying to reconfigure my end device in a non-desirable way. This will not only save time by configuring things automatically at a scale, but for sure will reduce the risk of issues in your solution due to configuration drifts. So far, you have seen how we can automate device configuration on applications following the GitOps approach in our end devices, and how the self-healing features made those configurations and workloads more reliable. But don't we have something similar for the base OS image? Well, if you paid attention, you will know that the answer is yes, thanks to something called Greenboot. Imagine that you have a running system in a windmill in the middle of a mountain. You decide to upgrade your operating system, and then, in the process, suddenly, nothing works. You don't even have access to the system to try to recover it. You will need to send someone to that remote mountain in an off-road track, probably, who knows how to connect and fix the issue. That means a lot of money and a lot of time. What if your system detects that failure or something is not working in the expected way and automatically rollbacks to the previous version where things were working correctly? That's possible thanks to OSTree images and Greenboot. Let's see it in action. Let's review the OSTree image definition file again. Here you can see the packages that are installed in the image. Do you remember that I said that I use a Python script with iNotify module to detect changes in the etc files? Here you can see that I installed the required package. If I update now the operating system image removing that package, it will stop working, so I need to prevent that from happening. We have Greenboot, which is a capability of RHEL OSTree systems that make possible to write your own personal health checks that need to be passed in order to mark an upgrade as successful. Let's take a look at it. But first, let me remove these packages and commit the change so the system starts building the image. Let's take a look to the Greenboot files. So remember that I have some configurations here in my source code repository, and Greenboot is one of them. I've deployed to the end devices this simple script that checks that all required packages for the self-healing subsystems are installed. And in case that they are not, the script fails. In this case, the script is under the required directory, which implies that if the script fails, the system will auto roll back to the previous image during the upgrade. You can also configure scripts that just send a warning message so you don't roll back the system in that case. In addition, I also configure a script under the red directory that will be executed in case of fail. So this script just sent a notification to Slack. Remember that I introduced a change into the image definition file. So let's review if the image is being created. Let me open the Ansible controller. Here in jobs, we can see that the image is being created. So let's wait a little bit more. The image was created. I will publish it so it can be used in the end systems, but before, let me show you something. Let me show how the system detects that there is a new OSTree image. Let's check if there is an upgrade now. OSTree upgrade preview. Okay, I hope that I didn't. Oh, let me check it. No updates available. Okay, now I will approve the publishing the new image and see what happens in the end system. So let's wait until it's published. Okay, now the image has been published, so let's check how the system see that there is a new version, okay? That where we remove Python 3 modules here. You can configure that when the system detects the new image, it automatically downloads and wait until reboot is applied to the system. Or even you can configure that the OSTree update just downloads the new image and also automatically reboot the system. In my case, I set this to be fully manual so we can better see the steps. Okay. Now I will update the system. So let me OSTree, I just remove here preview and we should be fine. Now it starts getting all the data from the image from the web server that is installed in the image builder, and that's it. Now we have to reboot our system to apply this new image. You have seen how I applied or download the new image from the end system, but you can also do it from the Ansible controller. For example, I created here a template that will update the OSTree image. Let me launch it. It will do the same thing that we did here manually, but I also include a reboot. So I will approve the reboot, and let me show to you the actual console. Now the system is rebooting. Let's wait a little bit for the reboot to happen. Okay, now what we are going to see is the system booting up, but right after finishing the reboot, it will reboot again, and it will do it 3 times. That's because by default, if Greenboot script fails, the system tries to auto-recover doing what all we know. That is the first troubleshooting step, rebooting your box. This time the reboot won't solve anything, so after the second reboot, it will start using the previous image. We can see in the pre-selected image in the grab menu. Here is 0, yeah, still 0, but in the next reboot it should be 1, which is the previous image version. So let's wait a little bit more. In the meanwhile, also let me show the here we can see the 1 selected in the grab menu and all the messages in the OSTree upgrades channel in Slack. Okay, now it should boot up the system because it's using the previous OSTree image version. Okay, there we go. So now we have our system running, but in the old image. If we log in into the end device again, So let me SSH again to the end device and perform amp rpm OSTree status. We can see here that we are running this dot means that it's running this commit. Once we also have a new commit here waiting to be applied. So we are working in the old with the old image version. You have seen an automatic operating system rollback, but what is more important is that you assure that the end device will be working as expected after the upgrade. I configured just a simple script that checks OS packages, but you can also write your own health checks that monitor the status for your applications right after the upgrade, or the connectivity, or any benchmark that you define. With Greenboot, you can create a truly bulletproof system upgrade. You won't find again problems like the ones I described before that imply high cost and delays in case of edge computing use cases. Well, we have seen a lot so far. We saw how we created a RHEL image by just defining it in a file descriptor located in a source code repository, how that image was deployed with a hands-off installation where there was no human interaction, and how besides that OS installation, the complete onboarding process was performed automatically in external tools such as Ansible controller. Then we saw how with just Podman, we created a serverless self-healing application with auto-updates enabled, using few system resources, which is a great benefit for edge computing systems. Then we configure our systems following the GitOps approach, enforcing the right configurations at the scale in our systems, assuring the consistency even in case of manual override locally. And finally, we saw how we prevent an OS system upgrade to break the desired behavior on our edge computing edge device by performing a system rollback automatically when a failure was detected. The demo showcased several compelling features and capabilities that promise to bring significant benefits to our edge computing solutions. For example, this simplified management. Ansible Automation Platform can help us to manage all our edge devices from one place. This makes things simple because we don't have to jangle between different points. It reduces how complicated things are and helps our teams to work better by giving them one place to set up, watch, and fix things. Efficient over-the-air updates. Keeping our edge device up to date can be tricky, but we have seen how it can be done more easily. This is important for keeping our device healthy and safe without us having to do it manually. This way, all our devices will run the newest software, making our system more secure and reliable. Platform consistency. Having all our devices using the same setup is really important. Ansible Automation Platform so it can be make every device following the same rules. And an attendant resiliency. If something goes wrong, Ansible Automation Platform and RHEL can handle it on their own. They can find the problems and fix them without needing a person to step in. This is super useful because it keeps our system running smoothly. So combining Ansible Automation Platform and RHEL give us an easier way to manage our devices, keeping them updated, making sure that they all work in the same way, and fixing issues without needing a person to jump in. These benefits are really important for our success in the world of edge computing. And that's all. You can find in this slide a link to the Ansible playbooks used to deploy the lab, so you can take a look if you want to check the details about the configurations or even if you want to deploy the lab on your own. And I also linked to an article that I wrote some time ago explaining the OSTree system concepts, including the rollback capabilities that we have seen in this demo. So, thank you for watching.